I'm going to introduce you to each of our presenters, and although they have been kind enough to list themselves alphabetically, I'm going to go from your right to left to introduce them as they are seated here at the table. They will be using a very different approach to the presentation. There will not be a lot of presentation per se. They want you to participate with them, and they will explain that as they get ready to go. So first of all, to my right is Percival Matthews. Percival recently joined the faculty here in the Department of Educational Psychologist as an assistant professor. His research investigates how symbol systems support mathematical cognition in order to gain insights into some underpinnings of human mathematical thought and some key mechanisms governing human symbolic capacities. He ultimately hopes that his research can inform effective pedagogical techniques, which really thrills me, that can be used to impact the life chances of everyday people. And as we learned on Monday, mathematical thinking has the potential to influence all aspects of human development, so I think that's really great that we're going to see some changes in pedagogy. Next is Ed Hubbard. He too is recently hired by Educational Psychology as an assistant professor. Ed's research bridges education and neuroscience through the use of brain imaging technologies. His interest is in how education builds specialized circuits in the brain for math and number, how differences in children may predict their successes or difficulties in learning math, and how different types of instruction might change brains in different ways. In addition, his work looks at how information from different sensory systems is combined to support learning and how it gives rise to the unusual experiences of synesthesia. And are you going to talk about that at all today?
Maybe tangentially if it comes up, but it's not part of what I'm planning on really talking about today.
I think it's really fascinating.
Do a separate talk about that.
Oh, cool, okay. Next to him is Martha Alabali. She is a professor in psychology, but she's also an affiliate of educational psychology, so it's ed psych all the time up here. She conducts research at the interface of cognitive psychology, developmental psychology, and mathematics education. Specifically, her research investigates mathematics learning and development with a special focus on the role of gesture. You going to talk about that today?
A little bit.
Good. Gesture in mathematical thinking and knowledge. She is also interested in the role of gesture in communication, particularly in educational settings. And last but certainly not least is Mitch Nathanson, who seems to be the busiest guy on campus. Mitch is a professor in the learning sciences area of educational psychology. He is a director of the director for the Center on Education and Work, and the director of an IES postdoctoral fellowship program in mathematical thinking, learning, and instruction. Mitch also holds a faculty appointment in the Department of Curriculum and Instruction, the Psychology Department, and WCER. See what I mean about being the busiest guy on campus? He is also a member of the UW's Cognitive Science Cluster and the Delta Program Steering Committee, a faculty member for the Latin American School for Education, Cognitive and Neurosciences, and a graduate and postdoctoral level summer school program sponsored by a graduate in, wait. You are a graduate of?
No, I think the
That is
the
the
Latin
program.
American School is
Okay,
a graduate
okay,
program.
which is a graduate program, the postdoctoral level summer school program sponsored by the James McDonald Foundation. Thank you. Your research is largely rooted in cognitive, embodied, and social science perspectives on learning and instruction in the STEM fields. He examines the nature of representations in both their internal, interpersonal, and external interpersonal forms as they serve meaning-making, individual and group design, instruction, reasoning, and problem-solving and learning. And he's a generally all-round happy guy because he also loves music making, biking, I almost thought it said baking, hiking, camping, and generally hanging out. So welcome, panel. I'm looking forward to your presentation. For the rest of you, they are going to want us to interact, so I have 2 microphones that I'm going to be circulating the room with as they ask for your interactions.
Hi, good morning, everybody, and thanks a lot for coming. I want to just say a few words about what we're doing here and how we've put this together. So you've seen a couple of other presentations this week where the panel members each got up and gave their own talks on their work, and the links were made between each of the talks. But what we're trying to do here is something that's a little more free form, a little more interactive, where we highlight certain problem areas, certain topics that we think have yielded interesting insights into how this big question of how education and neuroscience can start to come together. And places where this has worked relatively well, some places where there's a lot of work to do, and then also some ideas about potentially going forward, ways that we might try and approach this. And so, as was mentioned, my primary area is in the brain science part of this. But what we've done in getting the panel together really is trying to think about our common interests in mathematics as opposed to differences in the methodological approaches that we use. And so that's going to be the sort of overriding theme, is these common interests as opposed to these methodological differences. And first, we'll just sort of run through and let each person have a couple of minutes to say a little bit, aside from their formal bio, about how they're approaching these types of questions in mathematics and education, and thinking about the sort of broad themes that we're tackling today.
Hi, so I'm Percival Matthews, and I came to psychology in a weird sort of roundabout way. So I started off and I spent 5 years in grad school doing political theory. And so, there's always that question, art thou a reductionist? So there was something about looking at neuroscience that is in some way almost antithetical to a lot of what we do, or what we did there. And a lot of what we did was talk about how to make systems work, but part of what was missing for me was the empiricism on how humans think and how we tend to behave. And a lot of the work that I've been doing was in school, so I thought, well, I'll go to an education school, and okay, well, I'll do educational psych. And then the school where I liked my potential advisors the most, there wasn't actually an ed psych department, so I'll do developmental psych. And as I've gone in, I've come to be more and more towards cognitive side of developmental psych. So I've been going, more and more deeper inside the black box, but ultimately I'm really concerned with seeing what I can do to help contribute to what's going on in the classroom. Now, the classroom is this big, complex thing, right? So half your job as a teacher is to stop this kid from dipping this other kid's hair in ink. Or, you've got somebody who can barely read and somebody who's writing on a level like Shakespeare. And there are things that I don't have any kind of illusions about making easier. But there are things about the cognitive process that I think the more teachers know, the more it can help inform what they do, and we can lead to some pedagogies that are more effective. As far as neuroscience goes, you see lots of things in the popular media about neuroscience, and it just can overstate the case. But here are 3 things that I think neuroscience is great for, right? So my first year at Vanderbilt, as a graduate student, we had a bunch of math neural experts in, and we were talking about math this and math that, and eventually I asked what seemed to be maybe a stupid question. It was, what is math? And the simple answer, well, is what you do on a math test. And if you get to be a little bit more complex, somebody might say, well, it's a particular kind of talk, or it's a particular kind of praxis. But ultimately, a lot of what we're doing is this construct of math, which sometimes we define psychometrically, right, with these different measures. And what the neuro can help us do is help us get another way to look at this construct. So when you're defining it, you want to have multiple measures. So when you're doing this addition problem, or you're doing this multiplication problem, what are you doing in your brain that's different from when you're doing these other tasks? It's just another way to help triangulate. Second thing is, there's some early warning things that I think are really interesting. We know that if you can't read, you have serious problems in life. We're starting to understand now that math skills are seriously predictive of people's life chances. So we know now from brain readings, right? Not necessarily fMRI, but something like event-related potentials that are faster. If you have a kid 36 hours after birth, all right, and you do a change detection task on perceiving certain types of phonemes, you can get a little ways towards predicting whether or not this student will have dyslexia. And so traditionally, we waited until the kid was in first, second grade before we identified these issues. And some of the neuroscience is helping us go further back. The third big thing is once we start to understand some of these mechanisms, it can help us identify maybe not exactly what they do in the classroom, but we can understand some things that are maybe just bad, like maybe not having the kid exposed to certain phonological training. And so I think it has a lot of potential. It's got its limits, but it's got a lot of things that it can offer.
So I started out initially as an undergraduate major in cognitive science, which some of you may know, is this amalgamation of philosophy and psychology and neuroscience and computer science and linguistics and anthropology, and there's some education that was thrown into it occasionally, but it was really kind of this interdisciplinary field where people took very seriously the notion of trying to cross traditional boundaries and trying to bridge between different communities. And that sort of idea has guided me throughout. In the course of doing cognitive science, I became fascinated with an idea that Mitch is he talked about in his bio, this idea that high-level cognition fundamentally grounds out in our interactions, our physical interactions with the world around us, our embodied experience. And I started taking a sort of neuroscience approach to this and started using brain imaging technologies and worked my way up, basically. So I started out studying perceptual systems, basic perceptual systems about how we perceive the world around us, and then started to build up into higher level cognition. And one area where this is particularly interesting, I did some neuroimaging studies on the mental number line, and we'll talk about this. But as I started to do these studies of the mental number line, I started to ask, well, where do these circuits that we're measuring in adults actually even come from? So at that point, I started to think more seriously about this question of plasticity. So in neuroscience, we always talk about how the brain is plastic, how it changes in response to experience. And I started to take very seriously this question of plasticity and to say, well, what are the experiences that drive that plasticity? What are the experiences that build those circuits that we're talking about in adults? And at that point, I started to look more and more in depth at the particular educational experiences that children were having to try and drive the creation of those circuits. And in one particular area, I've looked at how does our sort of basic quantity system, our ability to understand that there's more stuff on the left or more stuff on the right. For example, right now I can tell that there are more people on my right than there are on my left here, without counting you guys. We can do this sort of thing. How does that then get linked up with number symbols? And so that's been an area that I've looked at more recently, looking at children between about kindergarten and third grade to try and explore that using these neuroimaging methods. So starting to explore those questions in this kind of bottom-up fashion of linking up neuroscience and education. And I think that, like Percival mentioned, there's a number of sort of limitations, and we want to be careful to not sort of go, well, this neuroscience is the end-all, be-all answer. But at the same time, there are places where neuroscience can be useful. And one that Percival didn't mention is there are times where cognitive theories based on behavioral data, based on observation, based on reaction times, all these sorts of things that you can do in a psychological setting may come to a loggerhead where the two of them both can account for the available data, but they really make these very different predictions about what the underlying mechanisms might be. And in those situations, neuroscience can help to adjudicate between these different sorts of ideas. And then, obviously, you're not going to be able to go just directly from brain scan to lesson plan. But once you've had that neuroscientific data, it then can feed back into a cognitive debate that then might inform approaches towards education and thinking about the types of instruction that would be most grounded in what we know from the cognitive theory. So that's one place where, I think that neuroscience can really play an important role in this sort of venture. So
I'm Martha Alibali, and my training was as a developmental psychologist. So I worked initially in a laboratory that focused on children's cognitive and language development. And also, in particular, my graduate advisor had studied language development in deaf children and had become very interested in the spontaneous gesture systems that deaf kids who weren't exposed to sign language were creating. This led her to an interest in the types of gestures and hand movements that typically developing children make in their early years as they learn language and as they start to learn other sorts of things. So I didn't initially start, as an educator or as someone interested in mathematics. But as it turned out, the particular project I got engaged in very early on was looking at the way that kids gestured when they talked about math problems, just as a context that was likely to elicit hand movements. And I've followed sort of both of these strands for many years until the present day, and both of these strands about this embodied sort of understanding that is expressed in kids' gestures and that might actually be in part learned via other individuals' gestures is an important theme in my work. But the initial focus on math problems, and in particular kids' understanding of certain symbols that we see in equations, in particular the equal sign, led me to start questioning certain things about how kids' understanding of these symbol systems develop. Now, gesture is kind of a symbol system, but it was a symbol system that also accompanies another symbol system, language, which was then being used to explain another symbol system, the inscriptions, the mathematical notation of equations that kids were working with at the board. And in this complex interplay of symbol systems, the meanings that kids gave to different symbols at different points in their development, the way they could talk and gesture about these symbols, the perceptual features of the problems and the way those were expressed in their gestures, all of these things seem potentially relevant and potentially important to understanding both how kids solve the problems, so their procedural knowledge about the problems, and also what they understood about the problems, their concepts, that the way they made meaning of those sorts of things. And so I look back on my very first research project as kind of a gift in that it really blended all these strands which I followed in intertwining ways and in separate ways through my program of research ever since. So I'm not trained as a neuroscientist. I've never done an imaging study, but I've lived in psychology departments all my academic life where there have been biological psychology programs and neuroscience, students with neuroscience interests. And so I've had a great deal of exposure to those kinds of information and that way of thinking. And I've watched as my own field, my own primary field of cognitive development has become much more neurally informed and much more embracing of a developmental cognitive neuroscience approach to understanding how development occurs. But I look back on my initial training in development as crucially important for thinking about this bridge between education and neuroscience. And that's a point that I think is actually important, that for educators and for understanding this interface, I believe that development is actually a really important strand. As I learned back in the very beginning, the study of development is the study of change. And often developmental psychologists are studying change, in typically developing kids as a function of age and not necessarily looking at educational practices and how those things might actually play into change. But education is also fundamentally a study of change. I mean, what we want is for kids to change their thinking, to acquire knowledge, to change their conceptual structures, to build conceptual structures that will inform their behavior in the world, in their everyday lives. And so these lessons about thinking about change, underlying processes, and things that might matter in change, it's really central in understanding education. Now, a second thing, though, so it's not just the study of change, a second thing that developmental psychology really takes seriously is the nature of the environment in which change occurs. So there's a big focus in the study of development on the social cultural context in which change occurs. And so, many of you have read Vygotsky over the years and thought about, the different layers of context, like Bronfenbrenner talked about, from the micro interactions that kids have day to day with their parents and teachers and peers, to the broader cultural context in which those interactions are situated, the values and the social structures that shape the kinds of experiences that kids have on a day-to-day basis. And so I believe that this appreciation for the social context in which development takes place is something that's crucially important in making this bridge, because education is fundamentally a social context, a social situation that's culturally informed and that creates different sorts of experiences. Different sorts of educational settings create different sorts of experiences that then lead to focusing on different kinds of perceptual information or different sorts of cognitive inputs or different kinds of opportunities for action. And all of these things, I believe, matter in the way that kids learn mathematics. And they're all things that we need to understand at a number of different levels, both at the more behavioral cognitive levels, which my work typically utilizes, but also at the more underlying neural sorts of levels, which others in this group study, that can help inform what's going on at the cognitive level. So from my perspective, I think that development is really one of the crucial pieces in this bridge from neuroscience to education. So.
Hi. So I actually started out in robotics and did a lot of work interested in things like object recognition and navigation with robotic systems, and that actually led me for a while to do some work in neuroscience, but not of the sort of cognitive elements that we're interested in, but more about the visual system, and gain a real appreciation for that. And I think everyone can really appreciate that we have all this wonderful specialized hardware, and there's a really question like, can we get there from here? And one of the things I will talk about, and I don't know if it'll come up in the other talks as directly, is this question of the bridge too far. Like, can we really construct an actual bridge that connects our understanding of the brain to our understanding of what goes on in classrooms, what goes on in teacher education programs, right? And at least some people feel that the bridge is too far, and so I'll explore that idea a little bit. But one of the issues I think that comes up that Ed already alluded to is that neuroscience may be particularly well suited to describe certain kinds of lower level, earlier developing kinds of systems which constantly reoccur throughout our lifespan and throughout many tasks, but we also construct many other kinds of functionality on top of that. And then as we get further and further away, it's a little bit perhaps by analogy to things like chemistry, physics, engineering. You know, how much do we need to worry about molecular issues when we're doing things like constructing bridges or constructing International Space Station, right? You know, yes, they matter at some level, but there's also whole branches of science that deal with their scale of the work that goes on as you construct things at a larger scale. And so science is always dealing with this issues of levels, and levels will come up somewhat in my discussions later. The other thing I guess I want to be sensitive to is that if we're going to sign on for this neuroscience and education agenda, we have to keep in mind that we're dealing with very limited resources that often get put toward education. And sometimes they seem to kind of, certainly in the area of research, they seem to pale in comparison to the resources that are available in basic research in the sciences. And so education seems to constantly be struggling for sort of credibility and struggling to attract those funds. And as we add more and more competition to that, what are we doing for the research that could be happening at these more macro scales? Like, how is that all going to be sort of allocated in a way that's fair, in a way that will ultimately really impact classrooms and impact teachers? So I think one of the big concerns I would raise, just sort of as in closing for these initial comments, is this sort of agenda of sort of mind, brain, and education, or neuroscience and education, lacks something I think is very significant, which is they lack a kind of theory of action, which is to say they lack a story about, if we do understand what these systems do at the neural level, how will this translate to changes in classrooms, changes in teaching? And it's a little bit of, in my view, of putting the cart before the horse, that, you know, we think if we sort of explore these basic phenomenon in sufficient detail, the answers will come. But the question is, should the research that's being done already be done in the context of a theory of action, so that we're doing the right kinds of research and we're going to impact the right kinds of practices and behaviors that actually will impact classrooms? So I'll raise those kinds of issues later too.
We're supposed to go on to the next slide, but I sort of want to jump in on a couple of things. So one of the points that Martha made, which I thought was really important, is this idea of different experiences and how those change cognition. We're also able now to start to see taking this point I made about plasticity, we can start to see that these different experiences are reflected in various different ways in the structure and the functioning of the brain. And so one sort of concern that often comes up with this sort of neuroscience approach is, well, let's say you see that something's in the brain. You see that there's a biological basis for it. Does this suddenly mean that there's nothing for teachers to do? Does this suddenly mean that they should just give up? And I think that the answer is a resounding no, that it's exactly the opposite, that what we're learning is that educational experiences and all of our experiences are reflected in the structure and the functioning of our brain. And so I think that the sort of one of the upshots of this is to demonstrate the sort of specificity. Oh, it's not just, you know, something about the entire brain, but it might just be a particular circuit in the brain that is behaving in different ways across different children. And then you can think about, you know, for example, different types of educational experiences. How do you target those circuits and these sorts of things? And the other thing that sort of leapt to mind as Mitch was speaking is, you know, this concern about funding and about sort of the perception of education. And so one thing that was really interesting, there was this conference on education and neuroscience last year, and they had the policy officer from the White House come, and he spoke. And one of the things that he said that's really interesting is that education as a field often struggles for credibility in DC because everybody and their brother who works in the government thinks that they know about education because they went to school, and obviously because having gone to school, they've learned a lot about how education should work. Most of this is based on their own limited experiences, based on their opinions. It's not based on any sort of science. And one of the things that he saw that was interesting is that as educators and psychologists and neuroscientists start to try and build these bridges, that people in DC suddenly have started to say, oh, well, I didn't know that math depended on the parietal lobe. And suddenly they lose this illusion of expertise, and that in some sense actually might be a powerful byproduct to this synergy between what's happening in education, psychology, and neurosciences, that it will remind people in DC that they actually don't know what they're talking about.
I strongly suspect that some people at different ends of the table are going to have some different takes on this. So when he said the parietal lobe, I think it's a really good transition to our first topical area.
Yeah.
So Ed's going to introduce really quickly a bit about the link between what we call, well, there we go.
Honestly.
There's always links.
There you go.
Oh, so the connection between neuroscience and math disabilities.
Yeah.
Do you want?
Yeah.
It
So
should
is
work
that?
now.
Is
Try one more time.
Yeah, it's working out. So, following up on Mitch's point about bridges, we found this great bridge that is mostly under construction. And you can see a little bit where it might go, and you can see where it's starting, and there might even be some sort of stepping stones across the way, but there's a lot of work. And this is a case, actually, in the science where we feel like we've actually got a pretty good handle on it. So if this is a pretty good handle on it, we still have a lot of work, and some of the rest of them, we might have even more work to do. And in particular, this idea comes from trying to take sort of the entire range of math abilities into consideration. And there's this term number sense that both the education community and the cognitive neuroscience, cognitive psychology community use. But once you start to dig into this number sense term, it turns out that the term is used in radically different ways. And Percival and I are co-teaching a course this semester that digs into all of these different sorts of things. So by and large, when people in the cognitive neuroscience community talk about number sense, they mean something very restricted, this kind of what they call approximate number system. And this is a system that we share with non-human animals. So you can see, for example, it's useful for a lion to know when it's outnumbered and go in a different direction. It's useful for different animals to know where there's more food or less food. So this seems to be something that is present based on behavioral studies and has a good rationale for why that basic ability to approximate quantities should be there, not just in humans. And we see that it's also present relatively early in development. Even in infants, we can show behavioral markers of this, ERP markers of it, basic sort of neural markers. But this is not math. This is the beginning, perhaps, of math. And then, and this is really kind of part of where we're thinking about this, you start to link up this system with language systems, with visuospatial systems, with body representations. And as you start to build through this, then you start to acquire all the different sorts of skills that we talk about. So things like counting, things like Arabic number symbols, using the fingers, eventually gestures on up through symbolic notation, word problems, calculus, topology, on up to, say, the proof of Fermat's last theorem. But this huge, and I've intentionally gone all the way from this to this, it's this huge sort of range. And the shading here from red to blue gives you some sense of where neuroscience has a good grasp on it, and where neuroscience has less of a grasp on it. So this echoes kind of Mitch's point about, you know, the neuroscientific methods work pretty well for some of these, but things like the years and years that Andrew Weil spent figuring out the proof of Fermat's last theorem is not necessarily amenable to the methods and the constraints that are present in a neuroimaging investigation. So there are certain things that probably we will never be able to run a proper fMRI study on. But at the same time, understanding some of these other systems may help us to shed light on this. And you might think that at a certain point, Mitch's point about the levels of explanation here will also start to kick in, that neuroscience might have a thread through some of this, and then it starts to become less and less clear how we can even design those sorts of studies and how those insights will be useful. But one place where we've been pretty successful in starting to make this link is in thinking about children who have difficulties with math and number, and one piece of evidence for it is this approximate number system. So what I'm going to do, actually, I don't remember how your animation worked.
I'm going to click a button and some dots are going to appear, some yellow and some blue, and you're going to tell us whether or not there are more yellow dots or blue dots, all right? You ready? Okay, here we go. All right, so you're right. So we're going to give you another one. You ready? Well, how many are there there? 6 to
4,
6 to 9? All right. So let's look at this next one. Ready? Which one are there more? You seem a little less sure.
8.
Ed?
I don't know.
Oh, well, there were more, I think there were more.
More yellow,
More yellow.
Now I
than
can
blue.
see what you're doing.
but the ratio.
Yeah.
Yeah.
So 8 to 7. 8 to 6. He's going to explain this.
So the idea here is that, as you guys saw, without counting, you're able to estimate the number of objects and to compare the number of objects. And this basic approximate ability to compare is dependent on the ratio between the two sets. So if you have more yellow dots and there's, say, 5 times more yellow dots, it's really easy. If you have just a couple more yellow dots, it's going to be hard. And we can show that it's the ratio by, if you say have 1 blue dot and 2 yellow dots, it's really easy. But if you say have 31 blue dots and 32 yellow dots, it's really difficult. So a difference of 1 dot is less or more important depending on how many dots there are. And this is a classic characteristic of sensory systems, not just for number, but for all sorts of other sensory systems. And the idea is that this sensory system, this ratio dependence, sort of gives rise to a number of our other abilities to be able to compare quantities. And then there are important individual differences in this system. And so this is a study that Justin Halberta and his colleagues did, where they looked at the precision of your ability to do this. So a small number here on what's called this Weber fraction, the ratio, is good performance. And then they compared this with a standardized test of math ability, the Woodcock-Johnson calculation test. And what you can see here is if you're good at this basic blue and yellow dots task, children, these are 14-year-old children that were tested on this, do well on math scores. And this was, interestingly, it was done retrospectively. So the math scores actually had been collected in kindergarten, first grade, second grade, third grade. This study had been going on for a number of years, and then Justin Halberta, Lisa Feigenson, and Michelle Mazzocco had the bright idea to say, hey, let's test them on this basic measure. And the correlation worked retrospectively here across these years and years of development, suggesting that there's something stable, but also raising a number of causal questions about, well, what drove this dot system to be good and what drove this education to be good.
And so with this Weber fraction, if you look at it on the left, that 0.12 means that you can discriminate basically 8 to 9, so a ratio of 8 to 9 dots. And on the far right, the 0.56 is much closer to a 20 to 40, closer to a 1 to 2 sort of ratio, or something.
Yeah.
14 to 25.
But the key point here is that given this sort of relationship, it suggests that one system depends on the other. But it's a correlation, so of course you can't necessarily infer the direction of causation, especially given the unique features of this study. So is education, for example, driving both this ANS system and performance on math? Is one foundational for the other? We think, based on a lot of other pieces of evidence, that one is foundational for the other, but we don't know that yet for sure. And then we can look to see what's happening in children who are having difficulties. So taking this point that Martha made about development, you can see that the precision of this approximate number system increases with age. So young children require a ratio of about, say, 2 to 1 here. And as they get older, that system improves drastically. By adulthood, you might be able to discriminate, say, 9 from 10. And they looked at children that were typically developing 5-year-olds, 10-year-olds, adults, and then looked at children that had been identified as having a specific difficulty in math and number. So these are children who were doing well in other areas, they had adequate opportunity to learn, all of these sorts of things, and yet they were still struggling, as assessed by a standardized test, they were still struggling with math and number. And they just looked to see, well, what was the precision of their approximate number system? And you can see here this red dot. These are 10-year-old children, and they don't perform like your typically developing 10-year-old children who are showing this level of precision here. They look more like the typically developing 5-year-old children. And you might ask, well, is this just because of, say, 1 or 2 children that are performing particularly bad? So you can see here this black curve, these are the adults, and this is the distribution of adults. So some of the adults are really good at this task. Some of the adults struggle a little bit more with this task. Most of them sort of fall in this middle ground here. So you can see the shape of the overall distribution of the estimates of the precision of the adults. 10-year-olds are not as good and also a little bit more variable. 5-year-olds also not as good and more variable. Now this red curve here you can see overlaps almost perfectly with the 5-year-olds. So it's not as if there's just a couple of children that were in this dyscalculic group that were performing worse. It's really the shape of the distribution, the overall sample here of dyscalculic kids looks like the sample of 5-year-olds. Yeah, Cheryl.
So I thought this when I saw the color, and now as we look at this, I think about some of the practices in special education that we've engaged in. And one of the things that we suspect with children, and we have no evidence, is that they have a hard time attending to the relevant aspects of the stimuli. So they are not really learning what we're trying to teach them. They're learning something else. Do you think that plays any role in this difficulty in being able to develop the number sense?
Yeah, so this is still an area that the people in the field themselves are still trying to understand. So one thing that happens whenever you have these sorts of dots is if you have all the dots be the same size and you have more dots, then the total surface area of the set that has more dots is also going to be larger than the total surface area of the set that has fewer dots. So is it, for example, that you're sensitive to the surface area as opposed to numerosity? Conversely, if I control for surface area, so I make sure that the total surface area of the yellow dots and the blue dots is the same independent of number, now the dots are different sizes. If In this particular case, they've done something nice, which is intermingle those dots. But if I had two separate arrays of dots, then you might also worry about the total extent that's covered by it. So there's all these continuous variables. This kind of goes back to a sort of Piagetian notion, right? These sorts of conservation of number tasks where if you have, say, 5 markers and you have 5 more markers, and then you spread them out, children will say, well, now there's more. And these sorts of, the sensitivity to these other features might be something that is important in trying to think about these sorts of number things. In these studies, they have controlled for that, but it's still unclear how much that might be still playing a role in the children who are struggling with this.
I think that question makes it a really good point for us to open it up for everybody because,
Yeah.
when you asked, are they attending to what they're supposed to be attending for? When you use a symbol, you have it, and it's intended to stand for a particular referent. So when you have a 5 and a 5 plus 5, it's not that it's necessarily supposed to stand for another just symbol 10, but there's something under it as far as an overall magnitude and relation that it's supposed to stand for. And so if for some students, he had a picture up, you've changed it back.
Oh, that one?
Yeah, one of the big things about this intravarietal fluxus that we're talking about is it's activated when people are thinking about approximate magnitudes that are tied to those numbers. And just like it applies when you're looking at those dot sets, you get tuned up so it applies when you're thinking about these symbolic numbers, these Arabic symbols. So it might be that they're seeing those symbols, but they aren't attending to what you want them to attend to, which is something about a sort of raw size or something. I don't know what you guys think about that or if it's relevant. Because one of the things that he just switched it back from the Woodcock Johnson. Sorry. One of the things that comes up is, this is significant, right? And in some of the studies, it'll explain the 20-some-odd% of the variance on the test. In some studies, it might be very significant and like 4% of the variance. And you're like, well, what about everything else? And so like Mitch said, are we going to spend a lot of money on certain types of neural imaging when there are all these other things that explain so much more of what's going on? If you're showing me 3% of the variance, maybe I can give this kid's mother some iodine or salt and it'll do that. So there are these issues. Anybody?
Good point, yeah.
Just jumping on Percival's point too about symbols. It's interesting to note that when we look at this, these distributions, the 10-year-olds look like typically developing 5-year-olds, so the age at which formal education with number symbols really starts. And so it's possible, given this data, and we still don't know yet, is it that, say, when these children who eventually were identified as having math learning difficulties, were these children, say, if you were to follow this curve, were they up here when they were 5? Or were they just like these kids until they started formal education? And did their brain then not respond in the typical ways once you start to acquire these number symbols and start to drive this notion of an exact quantity? So we've talked about how this number system is approximate, that it gives you a rough sense. Well, eventually we all learn that things like 4,532,311 is 1 unit different from 4,532,312. Now this requires symbols. This is a very different sort of thing from our basic approximate understanding of quantity. How does the first few years of education using those number symbols drive the acquisition of this different understanding of quantities, this exact, precise understanding of quantities? And how might that understanding of quantities as being these exact things, in turn, drive refinements in our sensory system? So can cognition basically drive the development of these basic perceptual capacities? And these are still open questions. And those are the types of questions where education might really play an important role.
And it's the sort of question that Martha's going to introduce to us next, right?
Yeah.
Yes,
Yeah.
exactly.
So I just want to say 2 more words about this slide, because we haven't really talked a little bit about this brain imaging study. But once you've got these sorts of notions, then you can go back and you can ask, say, for example, 12-year-old children, just to compare sets of dots and look to see, are there different regions of the brain that are responding differently? So these are typically developing 12-year-old kids. when they're presented with arrays of dots where the ratio is relatively hard. So they're struggling to do this. We all would struggle because they're close together. And this is just sets of dots. And their brain is responding more strongly on the hard trials than on the easy trials. So you can see this modulation by distance. Children with math learning difficulties, dyscalculic, are not showing this same modulation of this brain region. So this then says, well, hey, there's a biological basis to this. We can start to identify it. And it's not widespread throughout the entire brain. It's not that there's all sorts of differences. It's within these particular regions of the brain, right up in here. Basically, if you take your hands, put your palms on the bottom of your ears, and then see where your fingers fall, that's about the part of the brain that we're talking about. Right in there, this intraparietal sulcus region. And that part of the brain there is where we're seeing this. And this is where, when we do lots and lots of studies of math and number abilities, when we do lots and lots of studies of typically developing children and adults' abilities to, say, just compare sets of dots, this brain region time and time again shows up as being sort of the brain seat of our math and number abilities. And we even see that when we look at, say, similar regions in monkeys. So this seems to be a preserved circuit in the brain that's doing basic number abilities, and higher level math seems to depend on this. So if even at its most basic level, even at its most basic level, if this system is in some sense not responding typically, then you wonder about the entire cascade of things that might build on that. And yeah, David. No, I was going to say, and again, the question about sort of the top down also comes to play a role.
This led me to something I wanted to ask you, I think, a little bit earlier in terms of the value of the neuroscientific approach to this, which is that you can imagine, this is something I remember you talking about when you were here early on, was that this, and I just wanted to hear a comment whether you agree with this, which is at this point, since this is very stable location for this,
Yeah.
one could almost imagine that this would serve as a validity check to an intervention that one would want to try out. That is to say, if you had an intervention that trained this because we identify this as so centrally important, then in a sense, working backwards, we know that if the intervention is effective, a certain region of the brain ought to light up. And if it's not lighting up, the intervention may be lighting something else up, but it's not lighting up what it is that you wanted it to activate. Do you have a comment on that? Do you agree that or the larger question, I guess, is do you agree that the neuroscientific approach to educating the mathematical brain can also serve as something of a validity check to various interventions we may want to try out?
Yeah, so actually, this is great. We were just literally discussing this in our class yesterday, and we've spent 10 weeks getting them to the point of asking exactly that question. So that's good.
I think it's good.
It's good that
You got there right away.
yeah, exactly.
Let me just add one thing, and I
Yeah.
don't want to only be the skeptic here, but
yeah.
David's point is good on two counts, but there's also, I think, a really heavy caveat. Well, I mean,
Yeah.
maybe it's one major count, which is there's a way in which a lot of what we know about brain function is very good diagnostically, and it's less sometimes clear what the prescriptive role it can play. Kind of in the same way, when that bridge collapses, you can go in and study crystal structure and kind of figure out like why it sheared the way it did, but that wouldn't have led you to design the bridge in the first place necessarily, right?
Right.
Yeah.
So, but the other point is that, yes, that area is going to light up, but in terms of a lot of current methodology, it better not light up during baseline tasks. Like, it better be unique to that thing. Because if it's lighting up during baseline tasks and during your intended tasks, then it won't show up. Because a lot of the methods that sort of dominate current neuroimaging try to do these differencing things against some kind of baseline task. And so we don't actually know a lot about what's going on during those baseline tasks, unfortunately. And it turns out that a lot of stuff is probably going on based on the metabolic data. And so there's often a sense that we employ these things a little bit procedurally with the hopes that they will reveal exactly what you hope, but we don't really know very much.
There's also the issue that when you say validity, there are potentially other paths to get to the same end.
Yes.
And so if there's another path that you get that gets you to the level of competence, mathematical competence, it might not show the same structure because you took a different path. Does that make it less valid? It's not valid, and that is not showing that the kid is thinking through things exactly the same as whatever is normative right now. But it doesn't mean that A, there aren't alternative ways, or B, that the alternative ways aren't better than what we typically learn. There's a long way for us to go before we understand some of those questions.
Right. Well, I was actually going to make the very point that Percival was, that there could be compensatory approaches. So it may be that our intervention, as long as it's getting kids to be able to do the kinds of mathematical thinking we'd like them to do, whether it actually occurs in the particular brain region that it does in the normative case, may not actually be entirely important. So,
But
yeah.
So one way to think about this is possibly as a sort of, do you want to normalize the pattern of activity, or do you want to find compensatory mechanisms? And those might depend on different brain systems. So that might provide additional evidence as to whether or not what the intervention has done is to get children to do it pretty much the same way other people do, or they've found another way around it. There's classic examples, for example, in the neuroscience literature, of languages typically in the left hemisphere, people who have had one hemisphere of their brain removed, say, for epilepsy, or who lost one hemisphere of their brain near birth because of hydrocephalus. And yet these people go on to, with completely other brain areas and the other half of the brain, speak pretty well in occasional cases. So compensatory doesn't always mean that it's going to be necessarily a bad thing. But if, say, one level of math learning scaffolds another, and those particular mechanisms are important, then it might be, but we don't know that yet. So we don't want to make that sort of value judgment of, hey, this is the better way. But it starts to give us this additional layer of being able to understand at a mechanistic level whether we're, say, normalizing or invoking compensatory strategies. I saw a hand over here, yeah.
Yeah, I have a two-part question. The first one speaks to what you've been talking about. I've been involved in training people, some people who've had strokes, some people who've had lifelong learning disabilities, including in math. And one of the things that we do is to try to target the weaknesses. We start with the Woodcock-Johnson test, which is kind of redundant because as soon as you start working with them, it's apparent where the weakness is. But I'm wondering about the efficacy of training versus teaching, and for instance, using your dots.
Yeah.
What would happen if you just trained a person over and over with those dots? Does that improve, create some sort of plasticity or play off of plasticity and find new roots in the brain or make certain connections so that they actually get better at that task rather than totally compensating by saying, oh, this person isn't going to be any good at these dots, so let's try and see if they can be better at something else. And then the second part of it is NPR had a couple pop science things on learning recently, and interested in the intersection of them. One is that math connects with the pain location in the brain, so math
Or
is a
like the
pain.
insula.
Actually, no, this was math.
And
I know
the
what he's
sec-
talking about.
okay.
Stan Bialek knew.
And the
Stan
second
Bialek
part
talk
of
about
that,
math anxiety and the
Okay.
pain.
and the second part of that, how does that intersect with the umpteenth report on the Asian model of teaching, where you struggle versus the
Jim
American
Stigler,
where you
yeah.
praise and
Yeah.
yeah. So just kind of the intersection of those two things.
Maybe I'll jump in on the first question. I think Martha knows more about the second question. So one of the upshots of these types of findings is that perhaps the fundamental difficulties are occurring earlier than the things that we test with these standardized tests. So your point about, say, for example, training up on dots is actually one of the questions that we're starting to investigate as a field is, does training on this, one, lead to improvements in the ANS? And if it does lead to improvements, do those generalize? And the short answer is, so far, we are able to show that we can train the ANS but the evidence for transfer and to generalization is much more limited. So we're still struggling to understand, is it something about the training that we've missed a key thing, or is it that maybe you need to train and then have a certain amount of time to continue to build those circuits after you train? We don't yet know. But one idea here is this sort of notion of, hey, we're looking at Woodcock-Johnson. This is already a test of fairly sophisticated abilities. Even just mapping a symbol, just knowing that, say, this squiggly line stands for that many objects is actually a fairly sophisticated accomplishment. And if we're even asking about things like that, then maybe we need to look even lower, in the same way that the reading field has been pretty successful in trying to identify things.
Once you tackle the second part of his question, you should go ahead and go into
Go right.
another
Yep.
section, because
Yeah.
we
I'm
don't want to make
mindful
it
of the
seem
time.
like we just know everything here, and we only have like another 35
Okay,
minutes or so.
I will be happy to do that. So I just would like to say the work you're referring to about the math and the pain centers in the brain was actually looking at individuals with math anxiety. And what they showed was that individuals with high math anxiety, in the period of time when they were expecting to have to do a math task, actually showed activation in brain centers associated with physical pain. This was actually not the case once they started performing the task. It was okay. But it was in the anxiety evoked by knowing they were going to have to do a challenging math task actually showed that physical pain profile. And I think it sort of points to the fact that this area in which we're working is very complex. That's a more emotional kind of context that actually differs across individuals in important ways, but that affects performance potentially. In fact, I have a student here who's working on a senior thesis looking at math anxiety and how that affects people's ability to learn from a particular sort of instruction that we've seen is more beneficial for people with some sorts of attitudes towards math than others, instruction that involves comparing different approaches to a single problem. And so this whole question of how things like math anxiety or other sorts of attitudinal variables affect learning and performance, and how that modulates all the kinds of things we've been talking about. Does it modulate activation in the intraparietal sulcus while you're doing this sort of task? We don't know, and it kind of points to, I think, how broad the set of factors are that we need to really think about. The other data that you talked about, I think this is a report about, Jim Stigler was on NPR the other day talking about kids struggling in math, and in Asian classrooms it's much more typical for the child who's struggling to have to go to the board and sort of demonstrate their struggles to everybody else, and in American classrooms we're more worried about the child's self-esteem, and so we're not doing those sorts of things. I think that points to this issue, this point I was trying to make earlier about the social-cultural context. In an American cultural context, displaying your struggle in front of everyone is, embarrassing, and it's considered, potentially traumatic for the child. In the Asian cultural context, that's what happens all the time, and kids are used to that, and it's valued as a way of helping the child get to the point you want them to get to. And so the broader social cultural milieu influences the nature of the mathematical activities that kids perform, the nature of the things that we do in classrooms, the kinds of things that we take as appropriate for a mathematics lesson are not the same all around the world. And so I think that understanding, the kinds of things that we're talking about here with brain science are mostly studied in American kids who've had American sorts of upbringings, but, have they separated out the kids who had a Montessori education, or the kids who had kids who might have been educated elsewhere? Might those?
You do it if you're left-handed.
Yeah, well, right, exactly. So I think, and this will actually lay some of the groundwork for Mitch's questions about whether the bridge is too far. But before we get there, that's a good segue into this question about experience and how it matters. And so,
Sorry.
yeah.
Oh, yeah, I went all the way.
All right, so here we are. So in learning fundamental math concepts, children's experience matters a lot. And we know this, I study this from a behavioral sort of perspective. But of course, I believe that these differences are going to be manifest in the brain. And, the question is whether learning exactly how that is the case is going to be informative or important. So one of the things that we know is that the familiar actions and activities that children do in math-related contexts actually matter for the ways that they think about mathematics more broadly. And so I want you to consider a common board game like Chutes and Ladders. Some of us learned it with Snakes and Ladders, you know, the old version before the scarier version. But so this is a game that lots of kids play growing up, and they roll dice or spin a spinner, and they move along, and they count the squares as they're moving along. And Ed mentioned earlier this construct of the mental number line, which, you know, when we think about numbers as adults educated in the US with a particular sort of number line, typically we often think about numbers in terms of a number line, that bigger numbers are farther to the right and smaller numbers farther to the left. And one question is, you know, where does this come from? And does experience with things like Chutes and Ladders or board games where you move along the way actually feed into kids' understanding of numbers and their construction of the mental number line? So Bob Siegler and Geetha Ramani addressed this question in a series of studies that I think are really compelling and beautiful. And of course, in these actions, so they kind of boiled it down to a 1 to 10 sort of system here. It took out the chutes and the ladders and things that might have been extraneous. But they had one version that had numbers and another version that just had colors. And so in one version, kids rolled the dice, they said the numbers, they moved the pieces. And here you've got important correlations between actions, distance, so a larger number goes a farther distance along this linear path. And so all these things kind of coming together, so a number of discrete moves, the words that the children said, this is all sort of coming together. They brought kids in, actually low-income kids who didn't fare well on standardized tests of numerical abilities early on. And some of the kids performed with this 1 to 10 bear and rabbit game. Other kids did what I think of as the more Candyland version. If you have little kids, you might remember that Candyland, you just match the colors. You get a card that shows red, and you go to the next red square. And if you get a card that shows blue, you go to the next blue square. So you don't actually need to do numbers or count, and the colors are kind of randomly distributed. So they had a version that was color-based that didn't involve numbers, and they had kids do practice with these sorts of games. And before and after, they looked at counting, they looked at number reading, they looked at magnitude comparisons, so knowing which number is bigger, and they looked at kids' abilities to place a number on a number line, and found that experience with this sort of game actually led to measurable, with the number version, not the color version, led to measurable improvements in all of these sorts of skills. And also, in a later study, they looked at kids' abilities to do simple arithmetic operations with the numbers and also showed benefits there. They also then found correlations with the amount of board game play that kids did in their households early on, but not with the amount of video game play that they did, because it seems that this experience correlating number and space and action seemed important in the early development of this sort of notion. Now that suggests some sort of easy intervention things, and would those lead to, you know, the same sorts of brain structures that kids with different sorts of experiences might have ultimately for number? We really don't know, but we do know from the behavioral data that this sort of experience matters. So in my own work, I'm very interested in the notion of action, and so I realized that. So action and gesture, I've mentioned already, you know, the action in this game is sort of important. Kids moving along the number line, and in fact there are other sorts of interventions where you get kids moving around the classroom for number tasks. One question is how can we get at kids' understanding of action and the role of action, the way action is integrated into our adult mental representations of number concepts. And I believe that people's gestures are actually a really interesting and important window on those sorts of processes. This is data from Tyler Margitis, Rafael Nunez, and Benjamin Bergen that was presented this summer at the International Society for Gesture Studies. Basically, what they were showing here is when they had undergraduate students talking about certain sorts of mathematical concepts, that the nature of the gestures that the adults produced reflected two metaphors about number that had been previously posited on the basis of speech, but that we saw these also manifested in the gestural actions that people produce when talking about these things. The upper one shows arithmetic as collecting objects, and so people use grasping hand shapes and this sort of motion when they were talking about addition. The second one talks about addition as movement along a path. So you can think about having 3 and then adding 4. If you think about the mental number line, there's movement along a path in a particular direction. And they found evidence also of people's gestures manifesting these sorts of paths. And so this idea that there are these action-based mental representations that underlie what we typically think of as very abstract sorts of notions sort of gives a little window on the nature of the thinking that goes on, that our bodies are involved, that our experience of space and distance, that things like, moving the pieces on the board might actually help build those representations, because those action-based representations, which we later see in people's gestures, seem to be part of the basis of our notions of these very abstract things like arithmetic operations. And so I'm exploring these questions about action and gesture and also perceptual processes more broadly. Perception and action really together kind of make a loop that if we, I think, deeply understand perceptual processes, might actually come back to the question you raised earlier, Cheryl, about how do we know if kids are attending to what they should be attending to? How do we know if the nature of the action representations they activate in response to these things are the ones we'd like them to make? And so, thank you, forward, yes. So I just want to very briefly mention a couple of lines of work that are going on in my lab. We've looked at things like highlighting perceptual characteristics of problems, like the red equal sign that many kids have difficulty understanding, sometimes don't even seem to notice. They want to just add all the numbers and put the sum in the blank and not notice that the equal sign is actually there, maybe not where they're expecting to see it. By highlighting that perceptually, we can see differences in the nature of the problem solving that kids perform. By thinking about the particular actions that kids perform in a systematic way, we can help kids build action-based representations to connect to more abstract mathematical concepts. So here, a study going on in my lab that Christina was also involved in its very inception. Here we're looking at different ways of representing concepts via action and looking later at how that affects kids' performance and their gestures when they later talk about these concepts. So here we've got a child representing an equation with 2 buckets that have bean bags filled with fishing sinkers in them, actually. So they're representing each side of the equation with the weight of the bucket and really being an equation with their body and feeling the equivalence of the 2 sides of the equation by holding these 2 buckets of the same weight. We want to help them grasp this notion of the 2 sides of an equation. Other kids are building 2 Lego towers that are the same height, and so having a different sort of action-based experience of equivalence. And we're interested in understanding how these different ways of thinking about equivalence via action and via the body actually then play out in kids' later problem solving and in the way that they speak and gesture and reason about more symbolic sorts of problems. And so, we see lots of issues in the way kids, clearly this child over here is solving the problem incorrectly. But in order to sort of understand what the processes are that either bring the child to solve that problem correctly and then get that child to shift to a more correct sort of understanding, we're interested in these sorts of factors that have to do with perception and action and how those play in. And so that then raises a whole host of new questions for neuroscience that Ed has addressed in part in his work and that he's going to touch on briefly just now.
Yeah, I do want to keep this brief because I'm mindful of where we're at for time.
Give Mitch his time,
Yeah, but one of the things that we see that's really interesting when we start to think about these brain circuits for math and number relative to other brain circuits for other functions is where math kind of finds its neural niche in the brain. And when we look at, say, for example, brain areas that are involved when you do a subtraction task. This is now, instead of showing you slices through the brain, this is a sort of inflated, puffed up brain. And here, this is this classic intraparietal sulcus area that we see. But what's interesting is here's subtraction. And you see here's a brain region that's involved in moving your eyes around in space. And here are brain systems that are involved in grasping objects with your hands. So now you start to see at this brain level all the things that Martha's been talking about, these links between numbers and space, these links between gesture and grasping and calculation. And I would actually sort of flip this on its head a little bit, because this organization for number, for space, for grasping, for manual actions is not only present in numerate, literate, educated Western children, but is also present in macaque monkeys. So this is part of a primate brain organization, that we have these primate representations of space and action, and somehow intermingled in this are these representations of quantity. And so Bob Sigler has this great phrase when talking about these board games that he calls the wisdom of culture, that over generations of experience, parents and educators, we think about formal schooling as being something new. It's 200 years old. But of course, the basic ideas of teaching go back to Aristotle, go back to the Sumerians. So teaching has been around for a long time. And people have tried out lots of different ways of teaching things. Those things that work get passed on and continue. Those things that don't work have dropped by the wayside. They're in the dustbin of our cultural history. And part of what I'd want to argue, in fact, is that part of the reason these things like board games, gesture, these sorts of things are so ubiquitous in cultures, not only in Western cultures, but around the world. You can see board games like Chutes and Ladders in India long before the British came along. It's because of this kind of brain organization. So education both builds on our primate brain organization and then reinforces and strengthens the sorts of patterns of connections that are already there. So that's kind of the last thing I want to say about the neuroscience part. I see Cheryl's hand, Percy's gesturing.
So, just real quickly, is doing a really important piece of teaching the brain these things? So I'm thinking of kids with physical disabilities when I ask this question, who can't do for a variety of reasons. Can you represent these kinds of activities other ways other than doing?
I would say yes, that I think that seeing and experiencing, the perception action loop, I think we can access in a variety of ways. And so and the nature of the mental representations may differ, but I can either hold the buckets myself, or I can watch someone hold the buckets, or I can look at a balance scale. I think there are lots of ways to help get into these sorts of representations. I don't think they all require physical action, but I think if there is physical action, it might lead to something a little bit different in terms of the nature of the underlying representations.
And I think that, so there are two big thoughts I have immediately in response to just these last three different responses, right? So one has to do with, Martha talks about how maybe this action, maybe the seeing can help us understand these abstract concepts. Now, one of the words that we use there is abstract without stopping to think about what that means, right? So a lot of what we've been talking about today, we say math, we've been talking primarily about number and about quantity. And if the ways that we learn to understand about quantity really do go back to perception, if it's about perceiving some sort of magnitude, whether that's a bunch of dots or whether that's a line of a particular length, then we have to ask ourselves, to what extent are numbers really understood, particularly abstractly by most of us? Are these something that is actually a little bit more concrete? And as far as the cultural evolution of pedagogy, I think that there's a lot to the argument that things that survive had to work relatively well. But if you believe that there's some sort of teleology, that we're reaching the end, that we're reaching the most effective, then what you'd have to assume is that we've populated the entire space of possible things, and then we've whittled it down from there. If what we've done is populate a portion of the space that is sort of effective and whittled down within that, that doesn't mean that we've gotten anywhere near optimality necessarily. How do you go and optimize, and populate that entire space? We have to go back and start asking questions. So Martha has these bunching, gathering, and then we also have these paths, right? What's the difference between these discrete 1, 2, 3, 4 versus showing me a line of 4, right? Somebody tell me how to count to 4.25. Somebody show me how to count to pi. I can show you a circle, I can show you it with these continuous quantities. And so these are questions that we have to keep asking ourselves if we're going to start to populate the space of possible pedagogies. And start and also to think about whether these things are even abstract or concrete to begin with, what that means. And as we go up that abstract scale, as we go away from just number, right, which is a lot of math, how far this can or can't help. And I don't know, and I think that's going to get to part of what Mitch is going to bring up for us too.
I think that's actually the perfect
Yeah.
sequence.
Yes, right, all right. So,
So
So,
just
um,
one slide so we can go put
yeah,
yours up when
yeah,
you're
I think-
I didn't make the slide, but it's a kind of nice slide. Someone made it.
So we want to finish this part of it really by just sort of highlighting
So,
this.
yeah, I'll just make a few
Yeah.
brief comments. I guess
And then-
one is with respect to this idea of the bridge too far. So in 1997, John Brewer, who funds a considerable amount of cognitive neuroscience research, wrote this piece in Educational Researcher, and it's really taken on quite an important status, I think, in the fields in education and neuroscience, raising the question of whether what we really find as promising findings from neuroscience can really speak to education. And he raises a very skeptical lens on this work. He talks about things like early synaptogenesis, where you've got a proliferation of synaptic growth early on, and these notions of critical periods that if children don't learn certain things during certain times of their lives, they're less likely to learn them elsewhere. And he raises some of these important points that much of the research that is most well accepted is not done on humans, but done on other mammals and other animals, and whether we can really scale up from a lot of these data. Obviously, the field has moved forward since then, although even in his 2007 retrospective at ARA, you know, he still, I think, was concerned that the bridge was considerable. What he offered, though, as a prescription was to say, we don't need to build one bridge. We could ask about an intermediary bridge. And he proposed that cognitive science could be this bridge, because cognitive science is a behavioral field that also takes on a lot of the things that education folks are concerned about, but also takes on many of the concerns that neuroscientists are concerned about. And could this field be an intermediary? And this is sort of a point about why we have problems matching across these fields. And if you sort of know this notion, you can see that a lot of educational concerns tend to be in that sort of hours, days, and months kind of realm. This is a logarithmic scale. Laser.
It says laser.
Laser, there we go. And it is, in fact, a laser. Whereas a lot of the kind of phenomena that neuroscience is most well equipped to understand occurs down here. So, and of course the Simpsons is because they're good for everything. So I don't know, will this advance if I just hit?
Yes.
So one idea is to say that, you know, there's this sort of this spatial metaphor, right? You've got this, you know, island of neuroscientists working along, and you know, here's the sort of little peninsula of cognitive neuroscientists, and you know, here's education. And I actually kind of picked these numbers based on like sort of how many people are involved in these fields. So in an area like neuroscience, you've got the order of sort of tens of thousands, but in education, you've got tens of millions of people involved. Education is just much, much bigger. And then there's this idea like, well, we're going to build this, we're going to build this bridge, you know, but the problem that I see is neuroscience and cognitive science, they're already pretty close neighbors. They share a lot of views, most notably a view on reductionism. A view that that you can break down complex phenomena into these simple ones, study those simple ones in isolation with certain kinds of controls, certain kinds of methodology, and then sort of imagine how the pieces all go back together again. But education is very concerned not about reductionism, although of course it's hugely influenced by research in psychology, but about the whole child and about the whole system and about putting these things together. And in fact, it's a little bit misleading that just because they sort of maybe lie intermediary to them, that they're really going to be midway. I mean, this is really quite a large gap, and I think we've seen now for many decades the bridge between cognitive science and education is not all that well formed either. So it's not really clear once we get to here that we're going to make it across here, and then we end up with this kind of, you know, infinite regress potentially, you know, or asking about other fields that could be intermediaries. So really we need to be concerned that there's a weak bridge between cognitive science and education, even if cognitive science were going to play a role in making these bridges. And these are just some of the points about why cognitive science seems to fall short in many ways of leading to very prescriptive, very directly applicable kinds of contributions from its research. Seldom do cognitive scientists do research in classrooms. Seldom do they think about the very kinds of things that teachers and educational leaders most think about. There's often a huge gap between this notion of what the intended curriculum is and what's actually enacted in the classroom, and cognitive science has very poor models of kind of trying to think about these issues. And as I mentioned before, there's really no theory of action for how do you change teachers and how do you change classrooms. And I think this is quite profound in a way. Like, it's a really philosophical difference. In fact, cognitive scientists would never offer sort of prescriptions for what to do with learners without having first studied sort of baseline behavior of what learners actually do before you'd go and offer prescriptions of how to change that. But they do this all the time for teachers. They have no knowledge virtually of what teachers actually do in classrooms, but they're very quick to sort of prescribe new kind of behaviors and practices for teachers. So there's a real sort of philosophical mismatch that goes on between these things. There's certainly this issue of trying to articulate principles of cognitive science that are very well studied and can translate into ready practices. But we also have to deal with the fact that we don't know a lot about how these principles get implemented. And one of the big ones is teachers, when confronted with a lot of cognitive principles like practice effects and testing effects and integrating concrete ideas with the abstractions that you hope kids to learn, will typically say, oh, great, I already do that. I'm so glad to hear that research is out there because that's actually what I do. Teachers have a very easy time kind of already assuming that they satisfy these things, but the cognitive scientists would claim no. So the division really works on both sides. There's really enormous scale-up challenges, and there's very few successful scale-ups that we can really point to, and especially few scale-ups as you get to higher grades and higher order kind of cognitive things. And then finally, I guess the thing I want to sort of point out to, and this was also reflected in the talks that came yesterday for this American Education Week, which is there's a lot of emphasis, and it's certainly represented in this panel and in some of the other panels, on focusing on content area knowledge and what can neuroscience tell us about content area knowledge. And it actually may be that that's actually the least promising avenue to explore. In fact, one of some of the most promising things is to look at some of these things about impulse control and affect and things like that, where it seems like those have also large potential to influence children's learning and classroom behavior. The neuroscience fields are developing some very nice models of how those operate. But often that is sort of bumped off of the radar because it's not a disciplinary field. And so it doesn't sort of share this kind of conviction like, oh, education is about sort of teaching disciplinary knowledge, right? Teaching people how to be better self-regulators or teaching them how to deal with impulse control isn't really sort of it's not a standard, and it's not something we test. So, so it gets like a very peripheral kind of status in education, but it actually may be one of the most promising ways that neuroscience could be influencing education. So,
Mitchell?
yeah.
I really enjoyed your comments. I just wanted your reaction to something. I like the idea of bridge too far as opposed to Palin's a bridge to nowhere. So at least there's something to build toward. And what I'm curious about is your reaction to what you see as IES's goals here. I noticed
Like the
a
goal
little
structures
IES thing.
even?
In terms of the goal structure. It seems to me, I mean, this gets back to one of the very first things you said early on about the nature of funding. And I felt as you were talking a little bit more sanguine about this because IES, is in fact the source for this kind of thing, it seems to me at this point. Do you see the, IES investing more or less? I'm involved in IES as well, but from a completely different area.
Yeah.
How do you feel about where they're going, and do you think they could go further? Is there a way to increase the profile of this neurocognitive research program within IES's goals?
That's a great question, and I mean, I actually don't know if one looked at the portfolio of this is the U.S. Department of Education Institute of Educational Sciences, which is a huge source of education funding, and in some sense recent, like, last 12 years or something, like, so So prior to that, many of us went for funds through the National Science Foundation, which actually allocated a relatively small amount of money to education research. National Institutes of Health, which tended to focus on very early kinds of math and language because these were more obviously directly relevant to health issues. And also private foundations, which also tend to be quite small in comparison. And the amount of actual neuroscience research, I think, is really small, although I don't have any idea what those numbers are, but just being on panels, I can tell you that they're rare. So one thing that I think has been very beneficial in terms of IES is it has really underscored the role of education as a research field unto itself. And one of the ways this has played out that's very different than NSF is in the National Science Foundation funding. If you're interested in funding, if you're interested in proposing work on mathematics or engineering or something like that, I'm obliged as a social scientist to have an engineer on my research team. I'm obliged to have a mathematician on my research team because the National Science Foundation feels you need that disciplinary anchor. That's not a requirement in the U.S. Department of Education. Rather, they're willing to entertain a much more kind of social science rooted program of research. Not that they might not benefit from people in that, but quite honestly, it's not always clear what the disciplinary folks contribute other than making sure that, you know, the right aims are in mind, the right objectives for some kind of curricular intervention. But as far as actually carrying out the research and interpreting the data, it's often not clear what those contributions are. And I think IES, it's good that it moved away from that model, I think, in some ways. I think it's one of the things that could harm the National Science Foundation in a way. And the National Science Foundation doesn't require the complementary aspect of it, which is to say, you know, not to pick on engineers, but, you know, engineers can go off and propose an engineering education program, but never have any kind of social scientist or statistician or methodologist or anybody on their panel, and still, you know, receive perfectly fine sort of scores. So the idea that we are, you know, recognizing that the education of a disciplinary field is probably closer to a social science than it is to the disciplines themselves, I think is very important.
You know, I really liked what Mitch had to say about the bridge too far. There's another perspective, and that is once you get to Educationonia, right? What are the roads like in that town or in that country? And so he says that we don't know, if you go back one.
Back to Educationonia.
No, just one back.
Oh, one back.
This slide or the picture?
I'm at the very second, the penultimate slide.
Up, you went forward.
Sorry. How do
Get
you,
there.
I'll do it.
oh, I see.
So, if we are talking about, I can't even click on this. Oh, that's what it is.
There you go.
So, as far as do we know what goes on in classrooms? You know, within the field of education, one of the problems with IES, right, is we talk about fidelity of implementation when we're trying to figure out what we're giving here compared to what happens in the average classroom. Do we know what goes on in lots of classrooms? No. I mean, and to the extent that we're starting to get more and more, lots of times it happens to be a best practices classroom. Do we know what the average teacher does? I mean, if we think about it, lots of us educate teachers. So I came from Vanderbilt. We educate a lot of Vanderbilt teachers. Here we educate University of Wisconsin teachers, right? How do those people stack up to the multitude, the thousands of teachers that you see everywhere? So how much do we know about those connections and scale-ups in education? So if you have an intervention that's developed by, you know, teachers or people who train teachers, how do we know about how much that scales up? And I would say that some of those roads within that field of education aren't a lot stronger than some of these things that we're trying to build from CogSci. So I would just caution us not to throw out the baby with the bathwater, if only because we can think about a couple of times where it's worked out really well, right? So we're a long way from doing the math, but we're starting to figure out more about math. We've learned a lot, at the very least, about dyslexia and how early we can identify. And if there are a couple of things that we can find early, especially a couple of things that are cheap, that don't necessarily mean you have to go and scan everybody. If it means you can throw something on there and get a couple newer readings really fast. If we can show that this particular psychometric thing really well correlates really well with, you know, something that shows up consistently on an ERP or an fMRI, then that can go a very long way. And there's a lot of value to continue to try to build that bridge at the same time, we try to pave those roads in education. I don't know how to pronounce that. I'm not educational yet.
I took it from Groucho Marx.
I would agree with you guys to a certain extent, but I think you're thinking of education in a very monolithic way. I think that oftentimes when education is talked about, nobody thinks about special education and the work that has gone on in special education for decades, trying to bridge some of these fields. And in fact, I see special education as a stepping stone between the cognitive science world and the general education world. Many of the things that you're talking about as best practices, many of the things that you're talking about in terms of building competence in children have been the focus of special education research for decades, I'd say decades.
Yeah.
The one fear that I have with neuroscience is that in my experience, and I've been in the field for almost 40 years, is that when we find a biological basis for something, then everybody writes the child off. And so my caution would be that every time neuroscience comes up with a finding, that we need to stress, once again, the plasticity of the brain, and that there are things that can be done. And if I walk away from this week with nothing else, I walk away with, you can't blame the disability. You can't blame the lack of lighting up in the right part of the brain for a child's not learning. And that in fact, maybe we can light up other centers. Maybe we can find other techniques to help light up the appropriate centers. And maybe kids are going to not light up the right centers at all and do something completely different. But I just urge you as researchers not to forget that we've been at this a long time.
We had a big conversation the other day about the fear that, finding neural markers could become like a new eugenics on some level, where you write different kids off, where we say, if you aren't going this prescribed path right now, then you aren't ever going to. And I have a lot of fears about that.
Yeah. Yes. But I think one message of the things we've been saying here is that experience matters, and that the brain is plastic and shaped by experience, and so we need to understand how experience has contributed to those patterns in the biological substrate that we observe. It doesn't take experience away.
Which really tells me more than anything else, and I think our administrations have to be kicked in the shins over this, early childhood education is critical. Absolutely critical. I think about the research that was done with mothers of non-typically developing infants, and that mothers engage in differential responses to non-typically developing infants. So automatically, when the infant stops responding to the mother as the mother expects, mother engages in a different behavior. And so those children get years and years of different experiences than typically developing infants. And it says to me, we got to get in there. We've got to work with pediatricians. We've got to work with early childhood educators. We've got to get out and make sure that kids get the kinds of experiences they need to build from once they get to school.
They probably also need to train us on how to deal with the press.
I was going to say, just
There's
as
a
a
question over here as well.
just to make a point, is also we often will, again, be focused on certain aspects of the child at the exclusion of others. And so many times in this course of this summer school, we talk about things like nutrition, we talk about things like sleep and sleep cycles, all of which have enormous implications about how successful children are at school, but often they're outside of many of the conversations we have when we talk about education reform.
This is kind of a side tangent, so I'll keep it short. I just wanted to say that speaking sort of philosophically about the whole new eugenics thing, I can offer a little bit of anecdotal evidence that it doesn't have to be as scary as all that. My lab works with psychopathic inmates, and if there's any group that society writes off, I would say they're probably a pretty good example, because they're like, pure evil, whatever. And there's a treatment program across the lake at Mendota Juvenile Treatment Center that has done a pretty good job of taking kids who score high on psychopathy and actually helping them reintegrate with society, not by going with traditional punitive methods, but by going with methods that should make more sense in the context of what we know about how a psychopath's brain is different. And so when you know that there are differences in the brain, and you understand how that translates behaviorally and cognitively, what that means is you won't bang your head against the wall trying to use traditional methods of teaching. It means that you can actually start to switch gears to something that's more effective. So the whole idea of eugenics, it is, it could go that way, but I think that as long as we're, circumspect about it and we understand that what we're trying to do is help people, not write people off, then we can focus our resources in that direction.
Well, we're past our time. And unless you guys want to stay or everybody else wants to stay, I'd just like to start off by thanking you for, once again, a wonderful presentation.
Thank you.
Thank everybody for being here.